I'm here today with Mr. Prajwal Balasubramani, as well as Yorgos Burkitz, who will be presenting their work. Our first speaker will be Mr. Prajwal Balasubramani. Prajwal is a graduate research assistant at Purdue Center for Integrated Systems in Aerospace and is currently pursuing a PhD in aerospace engineering under Dr. Daniel De Laurentiis. His primary research interests are in the areas of systems and design engineering, multi-agent systems, mechanism design, and gamification. Mr. Balasubramani will be presenting his talk, Game Balance and Game Breaking, a Game Theory Approach. Prajwal, over to you.
Thank you, and thank you to everyone who's joined me here today morning. So I'm going to be talking about game balance and game breaking with a game theory approach. And I'd like to thank my advisor, Dr. Dan De Laurentiis, who has a session tomorrow too. So it's my first year at Purdue as a PhD student, and I'm very hopeful that this goes well. So jumping into my motivation and what my research question is, first we want to understand what game balance is, what am I talking about, and then look at if games are a good way to study system behavior and understand decision making within multi-agent systems. So are games important, and can they be used as research surrogates or modeling approaches? Essentially, games are agent-based models, and with the kind of computational capabilities that have been developed over the last few decades, games have increasingly become complex and have higher fidelity than before. And this increasing fidelity is generating some realism in games, so making the modeling approach more accurate. And this serves as a potential sandbox to test some hypotheses, which is what we will be doing in our work. Games have also been very vital in AI and ML innovations over the past 2 decades. For example, AlphaZero for chess or AlphaStar for StarCraft 2. And there are other agent-based games which are more commonly used for research, which is Progenitor X, which is a genetic engineering-based game, RoboCup Rescue, again, another systems engineering, multi-agent systems decision-making based game, MicroRTS, the one that we will be using, which is a real-time strategic game. And these games are also known as serious games and applied games. However, we will first need to understand what game balance is. And for that, let's look at a classic example of rock, paper, scissors, which is defined as one of the most balanced game. A balanced game is one where all players involved have the same probability to win, and the game has no bias over the players. However, in this game, if we do allow rock to beat both scissors and paper, it would produce an imbalanced game because the players are now biased to use one action space over the other two and always favor winning. For a game with only 3 mechanisms, it is quite easy to make the game balanced. However, games of larger scale struggle with this and end up causing some inherent imbalance that they contain. For example, Halo 3, which most of you might be aware of, a game in the early 2000s, had an overpowered gun that made it really easy to breeze through the game, which kind of left some love away from the game for the players who seek that frustration and the challenge in a game. With the construct of what game balance is, let's look at what our research questions are. And then the first one is game theory a good analytical tool to detect and evaluate game balance, and as in detect imbalances and evaluate where the balance lies? Which brings us to some subsequent questions, which is one of them is, do we expect dominant strategic equilibrium, which is a concept within game theory, to play a major role compared to Nash equilibrium? And how does knowing player preferences or rewards help in this assessment of game balance? And can this methodology be really applied to RTS games, where most of you, as you know, has a large number of decision trees and the game states are very large? And the second set of questions are led by the mechanism design aspect of our methodology, which is using mechanism design as a design of experiments approach effective, and specifically for our case? And are there any pitfalls in using this? And can this approach be applied to finite and zero-sum games as well? So with the research questions now constructed and a little bit of understanding about what game balance is, let's look at the approach and the setup by defining the framework, the game that we're using, and the design of experiments and the metrics that we're observing. So what you see here is a top-down approach of our model framework. So we start at the bottom, where we have the players defined for the game, and for our game we're using bots, which I will get into a little bit later. So we use rule-based heuristic agents as our players, and then based on the number of players we have and the kind of mechanisms that exist within a game, we set up a family of design of experiments, where one is developed after another based on the feedback we get from the topmost layer, which is the analysis layer. In this layer, the data from these tournaments or the design of experiment games are broken down into dominant strategy and Nash equilibrium, if there are any, and then that is applied on a game outcome analysis, from where we determine where the game balance exists, if there is a balance, if not, where the imbalance comes from. And then we use the same analysis outcome to then design the next set of DOEs using the mechanism design approach. And then this goes on until we are fairly confident with our game balance assessment. Just to talk a little bit about the game that we're using. It's called Micro RTS, which is a small implementation of a real-time strategy game, which was basically designed to perform AI research, test hypotheses in the early stages before we can move on to a bigger game where you can test it more specifically. It also comes with a few additional benefits that will help us along the way, which is that there's an easy availability and an easy ability to create bots for different testing purposes with unique set of strategy profiles. The game environment is also customizable, and then you can add in new mechanisms to create any specific game scenario that you'd want. Listed here in these three tables are the three components of the game, the agents, objects, and the actions. So the agents, of which there are only six, the base, the barracks, the workers, the heavy units, the light units, and the ranged units. The base is where you store resources and train workers. The barracks is where you train attacking units, and the workers are those that harvest minerals on the map for the player to use as resources to either build new buildings or create new units. The heavy, light, and ranged, as they speak for themselves, are the ability of attacks for those individual units. There are two main objects in the game: the minerals which the workers harvest, and the terrain which restricts movement of players. However, we will not be focusing on terrain in our effort. The last set of components, which are the actions that a player has, is whether to move, attack, harvest, train, or construct new buildings. At the player level, from if you can recall from our framework, as I mentioned, we will be using some bots, and 8 of those which we will be using are listed here, which are basically in two main categories: the rush and the defense. Again, as the word suggests, the rush category has four of these strategies where the player uses that specific type of unit to rush their opponent, and the defense strategies just use that specific type of player unit to defend. So how is game theory going to be used in this context? As we all know, game theory is a study of strategic interactions of agents that are self-interested within a system or a model, and in this case, a game in itself. It also deals with the preferences, states, informations, decisions, and outcomes of the game that the players go through. So one of the key concepts is best responses or replies, which basically mean that for a certain action that an opponent takes, what is our player going to do, and what is the best response they can come up with? So for every strategy that is existing on player A's side, player B would have a particular best response. What is a dominant strategic equilibrium? It plays off of the concept of best responses, but However, in this case, it is not for a specific strategy, but for the overall game itself. So all agents will follow the same behavior of choosing a reward maximizing strategy, irrespective of what the other player is doing. And any overlapping action spaces for both these players depicts that equilibrium. A Building on to dominant strategic equilibrium is another concept called weak dominant strategic equilibrium, where the players don't have a specific dominant strategy and their action space is equally weighted. So they don't have any bias over any of the actions that are available to them. So extending this example to rock, paper, scissors to understand it a little bit more clearly, we have the two players, one on the row and one on the column. And what happens when we analyze this through game theory is that all players are equally weighted on their decisions because the outcome for each of these, when they don't know what the other player is doing, is the same. So there is no specific bias in a balanced game, so which results in a weak dominant strategic equilibrium for the entire action space. So this brings us to a conclusion that for balanced game, there are two possible outcomes. One where the action space is resulting in dominant strategic equilibrium results in tie. For example, if the rock, paper, scissors game had only one action space, which would be rock and rock, or in the case where we looked at the imbalanced game where both players would prefer to use rock no matter what because they would win against paper and scissors, that resulted in a tie because both players used rock. So in that action space where the dominant strategic equilibrium exists, you get a tie. And the other case is when players observe all action spaces to be a weak dominant strategic equilibrium, as we see here. So now that we've understood the first half of our analysis layer, let's look at the feedback loop, which is where the mechanism design comes in, acting as the parent for our design of experiments. So mechanism design is a huge field and a subfield of microeconomics and game theory. It is a design of mechanisms, protocols, and institutions to satisfy a certain system-wide objective. It operates under two main assumptions: that the agents interacting within the system act in a self-interested manner, and then the agents may hold some private information that is relevant to make decisions for themselves. Mechanism design has been previously used in various fields to design protocols and institutions, which is what we will be using as our motivation to design our experiments. We make use of three main concepts within mechanism design: the social objective function, which defines the system-wide objective that all the agents or players involved in the game must comply. And then the player objective function, which is a personal preference that a particular player has in a given scenario. And then the Grim trigger, which helps us close the feedback loop within the DOE, which is it's a mechanism that is designed to trigger game states from their nature of repeatability. For example, if we have 100 games resulting in ties continuously, we can use a Grim trigger to change the repeatability of this game by either moving the balance towards one of the players, which is where the game breaking aspect comes from. So making use of the social objective function construct from mechanism design, our DOE is mainly classified into two families. The first of which is self-play games, where the players are institutionally restricted from using the same strategy against each other. For example, if player one is a light rush bot, then player two will also be a light rush bot, and so on for the other bots as well. And the other family is the crossplay, where there's such institutional rules of having to play the same strategy do not exist. And it allows the mix and match of player strategies for players. So light rush can go up against heavy rush and heavy rush against range rush and other bots that we have in the space. So to establish some baseline data, we run the game in an symmetric form that you can see on the right, which is a 16 cross 16 grid, where both players are given one worker and one base with 50 available minerals in green. And they are also symmetrically placed about the origin. So not a lot of difference in how the game starts. And what we do is then we build our DOE on top of this using mechanism design by changing the different mechanisms available within microRTS. So for the first family of design of experiments, we have the self-play games, which again is divided into two sections. The first one of which is a standalone game, where one of the players is held constant, like they begin in the baseline data. However, the other players, each mechanism is altered to see how that affects the outcome of the game. For example, resource quantity is varied for player 2, while player 1 stays in the same value as they were in the baseline data. So we inspect resource quantity, resource position, base position, and starting resources. So we vary the quantity of resources, or we move where the base is, or move where the resources are, and then we add extra resources that the player can start with that they don't have to mine, but is readily available to them. And the other half of the self-play games is asymmetric games, where we vary one of the aspects for player 1, but an opposing aspect for player 2. For example, in one of our DOE sets, we had resource quantities varied for player 1, but resource position, base position, and starting resources varied for the other player. This is to test out and tease any interdependencies between the mechanisms in the game. And the second set of DOE that we have is the cross-play games, which just has one generation, where we have the 8 different bots playing against each other in a full factorial. So with the model and the DOE complete, let's look at the kind of results we were able to obtain and answer some questions about whether microRTS is a balanced game from our perspective, and is using game theory a good approach to do this. So here is a result from one of the self-play game sets, testing the effect of resource quantity on the outcome of the game and how different it is from the baseline data. So what you see on the left is the 3 different generations we ran, where player 2 had different resource quantities, and how their results changed when we started to increase more and more. For example, one of the key things we observed is light defense, which is a bot that heavily depends on the available resources, had player 1 winning originally, but when we increased the resources available for player 2, we saw the outcomes turn around. So originally player 1 was winning, and then when player 2 had almost double the resources that player 1 had, player 2 ended up winning. However, from game theory analysis, we see that there is no dominant strategic equilibrium present in this case. So we can say that microRTS has some sort of an imbalance when we're testing out in terms of resource quantity. So the inference is that resource quantity controls where the game balance lies, and especially if a particular bot is dependent on that mechanism. Instead of bringing up such tables for all the different families we did, I've just summarized some of the other inferences we've gotten from testing the other mechanisms within the game. So resource position is a critical mechanism for game balance. The farther it is from a player's base, the higher the probability that the player is going to lose. And this is also kind of intuitive to us. So if our resource stock is farther away for us to go grab them, then we would consume more time in doing that than preparing to either defend or attack the other player. Base position is a sensitive mechanism for game balance. However, it is not critical. It's just sensitive. Slightest change can easily modify the win probability. However, we didn't see any specific case where it would completely turn over the game from one player to the other. The game run times drastically decreased with increase in starting resources. So this proves that starting resource is an impactful mechanism too, but no comment can be made on the extent of its control on game balance unless the run times of these games are analyzed. But with the current setup of our framework and analysis, we are not looking at metrics such as runtimes, and that's something that we would want to expand into going forward. So the conclusion from the self-play game design of experiments is that micro RTS is inherently imbalanced. So there is some imbalance that exists when in which was in the developmental stage of the game and has not been corrected, and then we cannot find an equilibrium in any of the symmetric games. Moving on to the asymmetric games, where we vary two different mechanisms for the two different players. RQ and RP, which is resource quantity and resource position, have opposing interdependency. So whichever player had the higher resource quantity would boost the probability of that player winning, and whichever had the closer resource position, that would boost the probability of win for that specific player. And that is also kind of intuitive, and we can understand that easily. Base position is a stronger contributing mechanism when compared against resource quantity. So our analysis shows that if you have a base closer to the resources and closer to the units on the map, you're more likely to win against a player who has higher resource quantity to you. Defense-based strategies are unaffected by this relation, however. And we're still working on trying to see why there's a difference in how each of these strategies depend on specific mechanisms. Uh, Starting resources, however, seem to be stronger than resource quantity, which also makes sense because if you're a player who already has 5 resources to begin with, uh, compared to another player who has 10 additional, but they have to mine them. So there's that time consumption aspect again. Moving to the last set of DOEs that we were inspecting, which is the cross-play games. On the left, you see a bar chart on the results of each of these bots when they played against each other. And then from that, we can see that worker defense has the highest balance based on the number of ties. And this is closely followed by range defense for the second most ties. And this is also very accurate with the nature of results we observed in the self-play games, which suggests that a range defense and worker defense bots, when played against each other or with other bots, have the most balanced strategies, and they're often able to have a fair gameplay.
Prajwal, we have about 2 minutes left.
Game tie rate suggests that heavy rush, worker rush, light rush, and heavy defenses are the least balanced. And the inference is that the defense strategies are more well balanced compared to the rush strategies. From a game theory perspective, the existence of dominant strategy equilibrium does not point to a balanced game, because neither there is a weak strategic equilibrium, or do these dominant strategy equilibrium end in ties. As you can clearly see, either one of the players wins and the other loses. However, we cannot make any comment on the number of equilibriums that exist has any impact on where the balance lies. So just rounding up with the research answers for the questions we posed at the beginning: is game theory a good analytical tool to detect and evaluate game balance? Yes, we certainly think so, because dominant strategic equilibrium has helped us detect some of the imbalance within the game. And do we expect this to play a major role over Nash equilibrium? We certainly do, because most dominant strategic equilibrium is more suitable for RTS games, as it turns out to be a zero-sum game for a game with 2 players. How does knowing players' preferences or rewards help us in game balance assessment? In zero-sum observable games like we have on our hands here, this would allow us to point to the best responses for each of the players. And with that knowledge, it is easy to determine what the dominant strategies are and where the equilibrium lies, if there are any. Can game theory be applied to RTS games, which was the most crucial question for us, because the number of decisions and game states in these games are very large. Yes, we certainly can, but however, the definition of the finiteness is something that is ambiguous, and we will have to look into when we expand into more complex games. Is using mechanism design as a DOE approach effective? Yes, it is, but then we need to have some precautions, and we need to consider some careful modeling. And some of the pitfalls that we observed, even though mechanism design and DOE complement each other, is that imbalances can arise from both players' side. So we don't know from which side they would arise. So such biases need to be considered before we start expanding on our set of experiments. Can mechanism design of experiments be applied to a finite non-zero sum game? Expanding on that question we had on the previous slide. As I said, finiteness of a game can be ambiguous and dependent on the computational capability on our hands. In our case, we just tested 4 mechanisms, but MicroRTS potentially has 9. So this needs to be further tested to confidently say that mechanism design is the best approach for design of experiments in finite games. Just leaving you guys here with what is left in our work until we show some positivity or complete positivity in our concept is we need to do a full factorial DOE for a complete assessment of the game, automate the use of mechanism design by using tools like optimal learning, and demonstrate game breaking with the understanding of game balance, and maybe even explore additional metrics like remaining game time to improve our assessment of game balance. With that, I will end and take any questions if there are any.
Thanks, Prajwal. We have one question, but we'll have to quickly answer and transition. So James Walsh asked, he understands that you are using bots, but is player experience considered for your observations?
Yeah, so this brings a very interesting point into the game, into this game balance assessment, which is the skill of a particular player. Since we did not want to have 2 players with different skill sets, we went with heuristic bots, which are almost equally matched. However, with the skill being one of the aspects within games and also eventually in systems engineering, we will have to modify our framework to make sure we account for that.
Wonderful. Thank you so much.
Thank you.